Imagine yourself in ancient times where the strength of humans and animals were the primary sources of energy. The toil of our ancestors powered the earliest civilizations, but soon, we began to harness the natural forces around us. The mighty rivers were tamed by water wheels, their ceaseless flow grinding grain and driving machinery. The unpredictable winds were caught by sails, propelling ships across vast oceans and turning the blades of windmills. But the thirst for energy grew as civilizations advanced. The Industrial Revolution marked a significant leap, transitioning from renewable sources like water and wind to an era defined by coal and oil. Steam engines roared to life, factories sprung up, and cities glowed with electric light. For the first time in history, we had the power to reshape the world on an unprecedented scale. In the past century, we've made yet another leap. We discovered how to harness the energy locked within the atom, giving birth to nuclear power. Despite its potential risks, nuclear energy has played a significant role in pushing the boundaries of our technological capabilities. Today, as a society, we're standing at another crossroads. We're witnessing a shift away from fossil fuels and towards renewable energy sources. Solar panels and wind turbines are becoming commonplace, and the dream of harnessing the almost limitless power of fusion is edging closer to reality. But as we look to the stars, we realize that our energy needs will continue to grow. To establish a serious human presence in the solar system, to build colonies on other planets, and to travel to distant stars, we'll need energy on a scale that's hard to fathom. Enter the realm of megastructures, concepts so vast and ambitious that they dwarf everything we've built before. One such idea is the Dyson Sphere, a structure that, if built, would encapsulate a star and harvest nearly all its energy. But are we capable of such a feat? Today, as we gaze into the cosmos, we find ourselves needing more energy than ever before. Picture the vast expanse of space and the immense energy requirements for a serious human presence in the solar system. As we venture beyond our blue planet, our energy needs skyrocket. Think about it. Powering habitats, fueling spacecraft, even producing food and water, it all requires energy, and lots of it. In the face of such demand, our traditional sources of energy fall short. They're finite, they're terrestrial, they're not built for the cosmos. So, where do we look? We look to the most abundant, the most powerful energy source in our solar system. Yes, we're talking about the sun, a massive nuclear fusion reactor producing staggering amounts of energy every second. It's an energy source that's been burning for over 4.5 billion years and will continue to do so for billions more. The sun, our star, holds the key to our energy needs. Have you ever imagined harnessing the full power of a star? It's a concept that seems straight out of a science fiction novel, but one that some believe could be within our reach. This is the idea of a Dyson Sphere, a colossal megastructure aimed at harvesting the energy of a star, a kind of solar power on an unimaginably grand scale. Now let's take a step back and consider the significance of this concept. Throughout human history, there have been moments of profound innovation that have utterly transformed our world. The discovery of fire, the invention of the wheel, the development of electricity. Each of these leaps forward has catapulted us into a new era of human civilization. The Dyson Sphere could represent another such leap. It's the epitome of thinking big, of pushing boundaries, of daring to dream in dimensions that dwarf our everyday lives. It's about reaching for the stars, quite literally, and transforming the way we think about energy. Imagine a shell or a swarm of structures enveloping a star, capturing its energy not just on one tiny planet, but in all directions. This is the vision of the Dyson Sphere. It's an idea that challenges our perception of what's possible, that invites us to gaze into the future and envision a world where the energy of the stars is at our fingertips. But, like all grand ideas, it's not without its hurdles. There are enormous technical challenges to overcome, from the sheer scale of the project to the materials required, not to mention the daunting task of construction. But then, every great leap forward has been met with skepticism, with doubt, and every time we've proven that human innovation knows no bounds. The Dyson Sphere, a concept so grand, it could very well be the next big thing in energy evolution. Now, you might be thinking, how can we possibly build such a structure around a star? Well, that's where the design comes into play. The initial idea of a Dyson Sphere was a solid shell completely enclosing a star, capturing all its energy. But that's a bit too far-fetched, even for our ambitious project. So, let's look at a more realistic design: the Dyson Swarm. Instead of one massive structure, imagine a swarm of solar collectors, each orbiting the star independently, like bees around a honeypot. These satellites would collectively harvest a significant portion of the star's energy while allowing for flexibility and scalability. The beauty of the Dyson swarm is its practicality. A catastrophic failure in one satellite doesn't spell doom for the entire project. Plus, it's a design that can grow organically, expanding as our energy needs and technological capabilities increase. So, a Dyson swarm, not a solid sphere, might be our best bet. Building a Dyson sphere will require materials beyond what we commonly use on Earth. We're talking about stepping into the future with materials like carbon nanotubes and graphene. These are substances that boast incredible strength, flexibility and heat resistance, characteristics that are indispensable for a structure designed to withstand the harsh conditions of space. But procuring these materials presents a challenge. Imagine the resources we would need to mine, refine and transport these materials on a cosmic scale. Now here's where our tiny neighbor Mercury comes into play. Its proximity to the sun and rich abundance of metals makes it a potential resource. Yet even with Mercury on our side, sourcing and transporting these materials will be no small feat. It's going to require advancements in technology, innovative strategies, and a whole lot of determination. The construction of a Dyson sphere will truly be a cosmic endeavor. In the harsh environment of space, simplicity and endurance are key. When we contemplate the design of a megastructure like a Dyson sphere, we must remember that it's not just about scale and energy capture, but also about resilience and longevity. In this unforgiving void, complexity is our enemy. A design that's straightforward, reliable, and easy to repair or replace is the blueprint for success. Think of a Dyson sphere not as a single massive structure, but as a swarm of countless simpler elements working in harmony, each contributing a small part to a greater whole. And what could be simpler and more enduring than mirrors? Large mirrors collecting and focusing the sun's energy are the heart of our Dyson sphere. Made from robust space-grade materials, they'll withstand the rigors of their solar proximity, while their sheer number ensures the system's overall endurance. Stripped down to basics, our Dyson sphere will be a testament to simplicity and endurance. There's a catch though. To build a Dyson sphere, we'll need energy, a lot of it. Now, here's where things get a bit ironic. We need a massive amount of energy to construct a structure that's designed to capture, well, a massive amount of energy. It's a paradox, really. But that's where our neighbor, Mercury, steps into the picture. Mercury, the smallest and innermost planet in our solar system, is also the closest to the sun. With its proximity to this colossal energy source, it's the perfect place to kickstart our construction efforts. By setting up solar collectors on Mercury, we can harness the sun's energy right at its doorstep. This energy can then fuel the production of our Dyson sphere components, powering the machinery and systems needed in the process. And there you have it, a solution to the energy paradox. We'll be using the sun's energy, transferred to Mercury, to build a megastructure that will ultimately harness even more of the sun's power. So we'll be using the sun to build a structure to harness the sun. Poetic, isn't it? Building a Dyson sphere won't be a manual job. It's a project of colossal proportions that calls for the most sophisticated technologies at our disposal. Robotics and artificial intelligence will be at the heart of this endeavor, taking on the gargantuan task of constructing this megastructure. Solar power collectors, automated miners, refiners, and launch systems, these are the essential technologies that will play a pivotal role. Picture this: solar collectors harnessing the sun's abundant energy, powering automated miners as they extract the necessary materials. These materials are then refined and fashioned into the components of our Dyson sphere. But the work doesn't stop there. Launch systems, guided by artificial intelligence, will then deploy these components into space. These systems will ensure each piece is perfectly positioned, creating a harmonious symphony of technology and engineering. The scale of this project is beyond human capacity, but with the power of automation, we turn impossibilities into possibilities. Automation will be our best friend in this colossal task. Now, how do we get these satellites into space? That's where advanced launch techniques come into play, like the use of electromagnetic railguns. Imagine a device that uses magnetic fields to generate an incredible thrust, propelling our satellite into the void without the need for traditional resource-consuming rockets. But the journey doesn't end there. Once our satellites reach their destined orbits, they need to unfold, much like a butterfly emerging from its cocoon. Picture a compact spacecraft, engineered to precision, unfolding into a massive solar collector. This isn't science fiction, it's a vision that's being pursued with fervor. Every satellite launched adds to our Dyson swarm, each one a small part of a grand design. With each successful deployment, we inch closer to harnessing the full power of the sun. One by one, our swarm will take form. Building a Dyson sphere is a process that gets faster with time. Think of it like a snowball rolling down a hill, gathering more snow and increasing in size and speed as it goes. This is the principle of exponential growth, the cornerstone of our Dyson Sphere construction strategy. We start small with a handful of automated machines on Mercury, mining resources, refining them, and launching the initial batch of swarm satellites. As these satellites spread out and begin to harness solar energy, we use that power to build more machines and more satellites. Each satellite begets more satellites, each machine creates more machines. The process accelerates. In terms of a timeline, well, the initial stages might take a few decades, but once the exponential growth kicks in, we could feasibly complete the Dyson sphere in a few centuries. It's a long game, but when you're playing for the future of humanity, it's worth the wait. Once our Dyson sphere is up and running, the sun's energy will be ours for the taking. But harnessing this power isn't the final step. We need to think about how to store and transfer this energy effectively. Imagine a swarm of satellites, each equipped with advanced solar collectors, capturing the sun's radiance. These colossal machines convert sunlight into usable energy, effectively becoming miniature power plants. But what about storage? We can look to cutting-edge technologies like high-capacity batteries or supercapacitors, capable of storing vast quantities of energy for later use. These would be crucial in ensuring a reliable power supply when the sun's rays are not directly available. Transferring energy back to Earth and other colonies would require equally innovative solutions. Concepts like microwave or laser-based power transmission could be key, turning energy into a beam of light or radio waves and sending it across the void of space. With the power of a star at our disposal, the possibilities are endless. It's possible that we're not the first to think of this. As we ponder the concept of Dyson spheres, we must also consider the possibility that other civilizations, far more advanced than ours, may have already embarked on this journey. Astronomers and scientists are always on the lookout for anomalies in the cosmos that could hint at the existence of such megastructures. In our search for extraterrestrial intelligence, we look for signs of advanced technology, and a Dyson sphere is a prime candidate. We use powerful telescopes to probe distant galaxies, searching for the faint glow of infrared radiation that a Dyson sphere might emit. This is no easy task, given the vast expanse of the universe. Imagine the implications if we were to find one. It would not only confirm the existence of intelligent life elsewhere, but it would also give us a glimpse of what we might become. Are we alone in the universe? A Dyson sphere might hold the answer. Building a Dyson sphere is not without its challenges. Yet these challenges are not insurmountable. We're talking about a global, an interstellar effort here. It's a project that demands unprecedented international cooperation. We'll need to pool our resources, our intellect, our technologies, and our resolve to accomplish this feat. Imagine the hurdles we'll face. The vast distances, the harsh conditions of space, the sheer magnitude of materials and energy required. But envision also the future that such a megastructure could influence. A future where energy scarcity is a thing of the past. A future where our civilization is not confined to a single planet, but spread across the solar system and perhaps one day even the galaxy. The Dyson sphere is more than a concept. It's a beacon, a testament to our potential as a species. It's a reminder that we are, in essence, explorers, innovators, pioneers. Together we can reach for the stars. We've come a long way from our humble beginnings, and the journey ahead is full of potential. Today, we've traveled through the evolution of energy, from the simplest forms harnessed by our ancestors to the unimaginable power of the sun. We've explored the concept of a Dyson sphere, a megastructure that could harness this energy and propel humanity into a new era of space exploration. We've examined the challenges and materials needed, the automation of construction, and the exponential growth that could make this dream a reality. The Dyson sphere represents not just a solution to our energy needs, but a testament to our collective imagination and ambition. It's a glimpse into a future where the boundaries of our capabilities are expanded beyond our current understanding. Thank you for joining us on this journey. If you enjoyed this video, please give it a like, leave a comment, and don't forget to subscribe to ScopeShift for more content like this. Stay curious and keep exploring.